Good evening, ladies and gentlemen, and welcome to the Lenape High School Project Lead the Way Engineering, Design, and Development Capstone Project presentations. Thank you for joining us this evening. My name is Joseph DeJulius, and I'm the Supervisor of Technology Education. Also joining us this evening is our Principal, Tony Catani, Project Lead the Way teachers Zach Bross, Mike Condorso, Sue Ann Miller, and Jim Scott, BAE engineers Robert Countess and Alex Whitney, and Ed Cohen from Vision Edge Software. Board of Education members and Superintendent of Schools Dr. Carol Birnbaum were unable to join us this evening, but we thank them for their ongoing support of our PLTW program. Special thanks to our sponsors, Lockheed Martin, BAE Systems, and Instinct Graphics for their generous donations. At this time, it is my pleasure to introduce our Master of Ceremonies, Mr. Mike Condorso.
Hello. Thank you, Joe. My name is Mr. Michael Condorso, as Joe said. I am one of 4 teachers in the Lenape PLTW program, and I have the pleasure of working with students during the first year and, again, as seniors in Engineering, Design, and Development. Engineering, Design, and Development is the capstone course in the PLTW High School Engineering program. It's an open-ended engineering research course where students work in teams to design and develop an original solution to a well-defined and justified open-ended problem by applying the engineering design process. Students perform research to select, define, and justify a problem. After carefully defining the design requirements and creating multiple solution approaches, students select an approach, create, and test their solution prototype. While progressing through the engineering design process, students worked with experts to hone their organizational, communication, interpersonal skills, their creative and problem-solving abilities, and their understanding of the design process. Tonight, the students will present and defend their original solution to the panel of experts that they worked with. There are 6 groups presenting tonight with a target presentation time of about 10 minutes per group. And without further ado, I would like to introduce Aiden and Alexa presenting Project Sapphire.
Good evening. I'm Alexa Zubrylov.
I'm Aiden Greenberg, and this is Project Sapphire Gamifying Procrastination. These are the topics that we're going to cover tonight.
Let's start with the problem. In 2010, the American Psychological Association reported that between 80 to 95% of college students in the US procrastinate on their schoolwork, which taxes the mental health and well-being of these students. Although there are resources for these students to combat their poor time management skills, these resources lack the combination of primarily positive, but also negative reinforcement recommended by the National Institute of Mental Health.
This section justifies why our problem is worth pursuing and how we came about our solution. 80% of college students confess to wasting 3 hours of their time each day. 75% of college students label themselves as procrastinators, and of that 75%, 50% procrastinate regularly and to a problematic degree, where their grades start slipping or they start losing substantial amounts of sleep to make up for wasted time. 33 studies covering 38,000 students found that procrastination was associated with lower grades.
There are many studies proving that procrastination negatively affects a student's mental health and well-being, as well as the quality of their education on the long term. After conducting marketplace research on around 100 high school students in New Jersey, we found that almost all spend a lot of time on electronics, and in most cases, more recreationally than productively. This shows that while these students can use electronics productively, they are unable to control their own recreational electronics time. So we decided to exploit this dysfunction that most teenagers have. If we could make an addicting enough app that relied on the user completing their school assignments, then the users of the app would be incentivized to get more work done at a quicker rate. This section details the design requirements we set for ourselves at the beginning of the project. If we were going to make an app, we determined that there are 4 design requirements that are absolutely essential: interactiveness, or how much the user actually interacts with the app, the inclusion of positive and negative reinforcement, and a unique functionality in the design and use of the app.
Once we had our design requirements, we could start planning out our app. Here are our initial concept drawings. All concepts were apps and included some sort of interactive element beyond just logging assignments. In the end, we decided that a combination of practically logging assignments and a pretty neat game was our best idea. The game would act as the perfect incentive for users to do their work. In order to advance further in the game, they would need keys that they could only obtain from logging assignments. A common question we got from professional feedback was why users couldn't just lie about having done an assignment in order to get keys. We've debated this issue several times throughout the course of the project and decided that ultimately Google Classroom integration would be the goal. However, given our limited time and skill, we decided that the honor system would suffice for now. Ultimately, if they got the app, they know they have a bad habit that they need to break, so it's up to them to use the app correctly to break that habit. With our plan in mind, we can begin discussing the execution of said plan.
We started by learning the basic syntax of C#, the language of choice for Unity and Xamarin. We did this through a free beginner online course on codeacademy.com. Our next steps were to start familiarizing ourselves with our respective development platforms, Unity and Xamarin. I did this by completing the Hello Android tutorial on Microsoft and making a demo app that translated phone words into phone numbers. Next, I started to develop our app and create the basic layout that we detailed in our concept drawings. I added basic assignments that students might encounter and want to log for keys. Throughout the past few months, the app has taken form. I added a key value display bar so the user can see how many keys they have, the value of which is read from a text file that Aiden also uses for his game. The assignment buttons all add different amounts of keys, depending on how work-intensive they are. For example, studying is only worth 1 key, while a project is worth 20. When the user clicks on the assignment buttons, keys are automatically added to the key value display, and an encouraging message such as "keep up the good work" is displayed. Also, when the menu at the top of the screen is clicked, it reveals a button that launches Aiden's incredible game. So with that, I'll hand it off to him.
Initial game development began with basic testing. Could I make a picture or sprite move around the map area? And that's what you're seeing above. This was more or less my Hello World or Hello Android, and where I was just 3 short months ago. Next, I animated a different sprite, and from there, it was time to create a new project and begin the actual game demo. This was the proof of concept prototype for a more fully fleshed out game in the future, and would give players a taste of what they could hope to one day experience. This was about a month or so later. At this point, I now had a brief map layout, a camera that followed the player, a health bar, a bow that shot arrows, and a couple bat enemies controlled by pathfinding AI. This was all thanks to various forums, APIs, and internet tutorials for basic game design. At this point, I was still very much a beginner with Unity. Even now, standing before you at Capstone, I'm still a beginner with Unity. This just goes to show how powerful and expansive the software truly is. One of the next major advancements of note is the save feature. This uses text files to save information about the locations and health of various entities that can later be accessed, as seen above. This works through the main and pause menus for loading and saving, respectively. Above is a cut-together video of the final demo. This contains AI-controlled bats and an AI-controlled skull, blueprints for future puzzles involving pushable crates, a locked door that can only be opened with keys from Alexa's app, and the start of a pretty neat boss fight. The boss can throw spinning axes and AI-controlled axes that will follow the player, the latter of which must be hit back at the boss in order to deal damage. Ultimately, there's a pretty nice showcase of what the game could one day be. The goal of this game being to hook the players. They can only go so far without keys, so this provides motivation for them to get their work done, log assignments, and get keys so they can play more of the game that they are ideally enjoying. And for those curious, above are most of the coding files for the stuff that I made, which total over 30 files at this point. Above is also an example of some code, this particular block coming from the script that controls the AI projectile fired by the boss. And if Mr. Bross is in the audience, he'll note that almost every line is commented just for him.
Both of our testing occurred in 2 phases. The first phase was the self-assessed quantitative testing, which consisted of a checklist of features that we each wanted to implement in the app and game. The second phase consists of the demos being sent to some individuals who were asked to complete a short survey regarding their experience. The next few slides contain the checklist of the various components of the app and game, with green indicating successful implementation, yellow indicating partial implementation, and orange indicating lack of success. The basic criteria for the home screen, key value display bar, and logging assignments buttons were achieved. They are all functioning as I wanted them to. However, I did not reach my ambitious goal of adding a timer. I was partially successful in implementing an app game handshake, as we each use the same text file to read keys from, and there is a button in my game that will launch Aiden's game.
The basic criteria for the main playable character, the bat enemies, and the skull enemy were successfully met. The basic criteria for the boss and map were also successfully met. The core progress features, save and load, were properly implemented. However, the startup menu does lack a title graphic, and the pause menu lacks a load game option. This can only be accessed from the main menu. However, that does not really detract from user experience. Currently, the game is only playable on the computer. It cannot be played on a smartphone. However, the menu buttons would theoretically work on a smartphone. And as Alexa mentioned, the foundation for the handshake does exist. The example being the text file that we both use for reading and writing key information. However, there has not yet been an attempt to formally link the two.
This was phase 2 of our testing process. My phase 2 testing consisted of sending the completed app to some individuals for feedback on the quality and aesthetics of the app. This feedback was collected via Google Forms and analyzed using Google Sheets.
My qualitative testing consisted of sending out a game demo and getting feedback via a survey. In the future, the testers' feedback could be used to improve the game, which would be a critical step in moving forward with game development.
Now that all our testing has concluded, we can analyze the results. Based on the feedback I received from the app testers, it is clear that a progress page that displays everything the user has logged over time would elevate the experience and increase the satisfaction of getting work done. Also, it was indicated that more branding using colors and icons would make the app more cohesive.
Based on the feedback I received from my testers, I know that I need to work on the pacing of the boss fight and ensure that the checkpoint before the boss room always works. Currently, trying to fight the boss more than twice may result in some bugs. Other minor changes include increasing bat enemy speed and rebalancing the weapons, or making sure weapons aren't too powerful. Finally, we'd like to extend our thanks and acknowledge the help we have received over the course of this project from several people, including Elizabeth Gia, Jay Casper, and of course our amazing Project Lead the Way teachers, Mr. Condorso, Mr. Scott, and Mr. Bross.
Thank you for taking the time to be here this evening.
Thank you, Aiden and Alexa. Presenting next with the dog fetch machine are Cherry, Krisha, and Sajan.
Hey everyone, I'm Cherry.
I'm Sajan.
And I'm Krisha.
And we're the presenters of the dog fetch machine. Our problem statement is that we want to solve the problem to save dogs that had health and physical issues without helping their owners. Through research, we found many justifications for this problem. We found that 54% of dogs were overweight in the US. We also found that dogs need about 30 minutes to 2 hours of exercise throughout the day, depending on their size. Furthermore, 15% of dogs' life expectancy were increased if they were fit and had more exercise. Some existing solutions that we found when researching were the Go.Go, which is a ball shooting device, the Keurig K9, which is a manual device that shoots a ring, and the iFetch dog toy, which is very similar to the Go.Go, but very small. For another piece of additional justification is that during the lockdown, that dogs are more likely to have stress, lower defenses, and more misbehaviors. This is due to them being by themselves without their owners and not being able to spend their energy. Veterinarians said the more they were able to go out, they were able to have less of these symptoms. So for our product requirements, we had two ideas. The ones that we thought were necessary and the ideas that we thought were just needed. So for the requirements, we wanted them to be safety because it's important that the dog would not get hurt. And we also wanted our shooter to be able to shoot in different directions and different speeds. For the planning, we had 3 different types of planning. The Gantt chart to show when and what we were going to do throughout the year. The testing procedure, which showed what we were going to test and how we were going to analyze it. And the parts list, which is a list of the parts we were going to order before our testing to make sure we had everything before testing. And these are the initial sketches we had for the designs. This is mine. This is Krisha's. And this is Sajan's. And this is the design matrix that we used in order to designed the criteria to choose the best design. Here you can see the final scores are 36, 36, and 35. After this, we decided to go with Sajin's idea for the base design to make, because he had the most reliable design shooter. So for our proposed solution, we wanted to have an autonomous device that used 2 motors to shoot balls in different directions and different speeds randomly. We also had a treat dispenser, which would allow for a positive feedback loop for the dog to make sure that it would be more engaged with the system.
For the design of our product, we had 2 iterations. Our first iteration was our initial design, and this holds the 2-wheel propulsion system and the treat dispenser with a flap. As the year went on, we found that changes needed to make, which brings us to our second iteration. The biggest difference in the dog fetch machine as a whole is the stronger motors, and then for the treat dispenser, we completely redesigned it, which will be explained later. Moving on to the construction of the prototype, we split our construction into the construction of the fetch machine and the construction of the treat dispenser, as we did not have time to integrate them together. For the fetch machine, we started off by cutting, drilling, and assembling our frame. Then we moved on to cutting the acrylic with a laser cutter, and the acrylic pieces include things like our hopper system and our motor attachment plates. We then attached those as well, bringing us to the motor attachment phase, where we also conducted testing and found that our original motor choice were not powerful enough to shoot the ball, so we upgraded our motors.
For the controls aspects of our machine, we used a rev expansion hub, a rev motor, and 2 Android phones. The expansion hub was used because it had a direct Wi-Fi system, which allowed us to use a non-external power source. This allowed us to test outside and not need them. For the rev motor, we decided to use this because it had a very high power of 6,000 RPMs, which would allow us to shoot very far. And the 2 Android phones were used because they were enabled us to use on-bot Java, which can be used along with the rev hub to transfer code very quickly onto our computers and our system. The on-bot Java allowed us to make quick changes during testing. For the code for the shooter, we decided to create an array which held different speeds, and then it would be sent to the motors. We also used a random class to randomize the direction and speed of the motors, or the balls. To do this, we changed the speed of the motors so that one wheel would be faster than the other, changing the direction.
Moving on to the construction of the treat dispenser. For the first phase, this is our first design. We laser cut our pieces, assembled them, and as we tested, we found we did not have fine-tuned control over the treat dispensing, so we moved on to our redesign. Before we decided to laser cut our redesign out, we decided to model the apparatus and the mechanism to make sure it worked before we spent the time laser cutting pieces again. And then after we found the mechanism acceptable, we laser cut it out, assembled it, and started to add electronics. We used a motor, potentiometer to set the dispensing threshold, which is how many times the ball needs to be retrieved before a treat is dispensed, an ultrasonic sensor, which would be attached right before the wheels on the dog fetch machine to detect if a ball has been returned. And then this is a test of the treat dispenser working. In the test, the dispense threshold is set at 4 using the potentiometer, and my hands representing what the ball would have done, which is cross the ultrasonic sensor. And after 4 times, a treat is dispensed.
So for testing with our shooter mechanism, we had 3 different phases. We started with planning, which we used a Gantt chart, as Cherry mentioned before. We decided we wanted to test with and without a dog. So for testing without a dog, we decided to test in our school courtyard during class, and we were able to test for direction and distance. So we were able to get 20 tests, and we got a max distance of 53 feet, which was within our standards. And now with a dog, we got to test with my friend's dog, Daisy, and we were able to find that the max distance was 50 feet within 10 tests, and you can see that I loaded the ball manually and Daisy went to fetch. For the results without the dog, you can see on the top table that our beginning results were kind of lower, and then you can see as we got more tests in, you can see that our results slowly got farther and farther. And you can also see that we recorded the direction where L is for left, S is for straight, and R is for right. Now with the dog, you can see that we had a fetch rate of 100%, but we had a return rate of 0% because Daisy is still a puppy and she doesn't know how to return the ball yet. So direction, we also tested, and you can see that right here. And for our analysis, we decided to, we figured that both of our parts worked great individually without integration. However, the optimal situation would have been that the treat dispenser encourages constant engagement with Daisy or any other dog to return the ball back to the shooter every time. And now for future improvements, we would like to obviously integrate the two systems together. To complete our device, we would like to add safety features, which would be 3D printing a cover for the machine to avoid any dangerous situations like electrical short circuits, or while a child is playing around it, or also for the dog. So we would also like to make it autonomous completely so that the dog is the only individual that interacts with the machine using sensors and timing. And we would also like to put it on wheels to make it family friendly, and human users could also drive it around like an RC car so that they could also have fun with it. And thank you for listening.
Well done. Presenting next is going to be Ian and Mackenzie presenting the Shot Put Buddy.
My name is Ian Camerata.
My name is Mackenzie Lippincott, and our project is the Shot Put Buddy.
So the problem statement. The current way that shot put throws are measured is a time-consuming, high-effort, and a costly process. As a thrower for the last 6 years, I can tell you that even at the highest level meets, it takes up to 12 seconds to measure a shot put throw. And when you're alone or at a typical high school meet, it can take up to 30 seconds. This may not seem like a lot of time, but over the course of a meet, which can have about 100 throws, this can add up to an extra 30 minutes.
We had a ethical justification to our project. Being a referee for throws is typically very dangerous, having an implement coming at you or towards you. And we had a survey that showed about 1/3 of athletes, coaches, and referees have heard of or seen someone who has gotten hit or hurt with an implement. And we felt that it needed to be something that should be implemented so people can be safer during these events.
An additional justification besides just injury is also the lawsuits that evolved from this. Many people who get hit, they'll try to sue the venue, such as a referee who tried to sue the University of Texas after being hit in the head with a shot put, as well as a boy who was retrieving, and a second thrower began to throw and he got hit. The problem with these lawsuits is that they typically never pay out, and these people end up having to front their own medical bills, as well as being very bad publicity for the universities.
We considered some alternative solutions that already existed. For example, the laser links, which is a laser measurement device, but this turns out to be very costly and can total to over $3,000, and it also requires a certification of training to be able to use it, which can be very complicated for schools to be able to implement into their events that they host. There was also the MF Athletic laser measuring device, which was well over $1,000 and required the same certifications. And then there was the Gale Athletics. They provide many different measuring tools, including laser measurement or the basic tape measurement. And we felt that we could come up with a better solution than what they have.
So some of our constraints, the top one would be time. We had to finish by May 23rd. Our budget had to be under $150. We were limited to things we can get in the classroom primarily. The setup time had to be underneath 20 minutes. It had to be visually appealing to others, and it must be able to withstand the impact of being thrown multiple times.
For our design goals, we had 5 different goals that consisted of accuracy, time, if it was a legal shot,
an even balance of the distribution and the weight of the shot put, and the aesthetics, how it appeals and everything. Validation, we would validate this through many surveys, testing, and we would determine success through the surveys and our testing to determine if they are accurate, if it looks nice, the durability, and how long it took to measure the shot. For our prototyping design, we originally thought we would have a capsule that would insert into the shot put, and it would screw in, and it would communicate with the laptop to send the results of the throw over to it. We kind of had some problems with this, just doing a capsule that would insert halfway through, because it would offset the balance of the weight of the shot put. So at some point we changed it so that we would bore a hole all the way through, and the capsule would screw in that way.
So some project pivot points we had. Our original idea was to use a Wi-Fi sensor, which is pictured here, and that would be inside the shot. It would transmit the data from a vibration sensor to an Arduino outside of the shot, which would calculate all of the distance with the accelerometer as well. Unfortunately, we could not get that to work, so we made the transition to radio transmitters, which we did get to work in the end, except we had to include an Arduino inside the shot put as well for this. And then another pivot we had to make was, instead of using an accelerometer to measure distance, unfortunately we had to scrap that for the time being. We have it set more for safety now, so to tell you whether the shot put has hit the ground or not and if it is safe to cross the sector. However, we believe that if we had more time, we would be able to include this. So here's our construction. This top bit right here, that is the receiver that works on the outside of the shot put. It's connected to the laptop, and what this does is it displays whether it is safe to cross the sector or not safe. And then this is the transmitter circuit, and then this right here in the breadboard, that is the vibration sensor. And what that vibration sensor does is when it hits the ground, it detects that it has hit the ground, and it says a signal saying, I have hit the ground. And that is what's displayed, and if it has not detected a value, then it will say that it is not safe to cross the sector and you cannot go.
For our prototyping testing plan, we had originally planned to insert a capsule into the shot put, but with the materials we have, we were unable to fit something that would be able to insert in it with the size of the different circuitry we had. So we would have a rectangular object that would have all the circuitry and everything in it that would communicate with the computer inserted into a similarly sized item to a shot put, since a shot put is solid iron and it would be hard to drill into it with the materials we had at school. From there, we would throw the dodgeball several times to ensure it would measure properly and it would calculate distance. And we would also incorporate how long it would take for the shot to be measured, as well as the communication between the shot and the computer. For our data collection, the shot put would send the data collected from the throw to the coordinating Arduino connected to the computer, which would then be implemented into an Excel sheet where formulas would be used to calculate the final distance. And all the data from the entire shot throw would be recorded in the Excel spreadsheet.
So here's our code. The code on the right, this is the receiver code. It's pretty simple. This top bit right here is just an error code saying if we do not detect a transmitter, display this. And then this bottom code is saying whatever data is detected from the transmitter, display that on the screen. And then right here, this is the code for the transmitter. So this top bit is just the code libraries and everything. And then it's basically just an if-else statement. So if the vibration sensor detects a value over 10, display it is safe to cross because we know the shot put has hit the ground. And if it has not, display a value that says it is not safe because the shot has not hit the ground yet. Here's our video. So what this is basically showing is that's just the setup right there. As you can see on the screen, it's saying not safe. And then I'm going to bang it on the table. It's saying a value, it's safe right there. It's going to wait 15 seconds, which is a good amount of time for anybody who has to cross the field or for the referee to get out in the field. And then, as you can see, this is going to turn back on in a second, start saying not safe again. There we go. and then say another throw happens. As I bang it on the table again, it's going to say it's safe, and it's going to pause for another 15 seconds. So the analysis of results, in the end, we did not get it to measure distance. However, we do believe that we have accomplished the goal of making shot put a safer sport, as we now have a warning system of whether it is safe or not to cross the sector. The setup is under 20 minutes. It was under budget. We were on time. And that's about it, yeah. Thank you for watching.
Thank you, Ian and Mackenzie. I would say that was an on-point presentation if I brought some of my puns in. Presenting next, Caden and Vish are going to be presenting the Effective Future Enforcement Conduct Tool.
Hello, my name is Vishwas Patlola.
And I'm Caden Conklin.
And we'll be presenting the EFFECT, the Engineered Future Enforcement Conduct Tool. The problem statement. Due to recent controversies, long-standing public outcry, the fact that about 27% of officers have pulled their service weapon out before, and because of the inconsistencies and expenses of body camera systems, a new detection system could be used to change the climate of policing forever. A new device/system could help to create a better understanding of actions during an incident, try to record and inspect actions, and overall create better trust between law enforcement and the public. Some statistics. According to a study from Pew Research, 27% of officers have had to fire their firearm before on duty. 80% of large police departments do have body cameras as of 2016. Sadly, as of 2016, only 31% of small departments have body camera systems. On average, police body camera prices vary from $400 to $800 per piece. However, there's also other storage costs as well. Only 5 states currently require the mandate of the use of body cameras, and the number of law enforcement-related shootings and complaints have increased over the past 8 years.
Of course, when anything is being created, there needs to be a reason why. So we have split those reasons into 4 different sections. The first section is technology. So each police department has their own rules and regulations regarding body cameras, and there is not a set system. Along with this, not every department even requires full-time usage of body cameras, and what footage is recorded is kept confidential for the most part. And at this moment, about only 50% of smaller police departments have the ability to pay for body cameras. The next section is legal. In 2020, the Supreme Court ruled in favor of removing immunity in ongoing police conduct cases, showing that there is an increase in awareness of this situation. The next section is informational. We want to make sure that the public has information to what is going on within the police department, and hopefully this will create a better relationship between the public and the police department itself. And lastly, for health and safety, due to the rise in fatal police shootings, we need to create a system in which all the police departments can stay on a standard rule system to make sure everything runs smoothly.
Now, the big question. How do you create a device for a situation and a problem so varied, such as police detection and surveillance systems? Well, you've got to start with the standard status quo out. After 2014, body cameras have become the norm because that's when they were first put into large-scale implementation. As you know, body cameras cover from waist or from chest rigs. And as stated before, many large departments have body cameras, and an increasing number of small departments are getting body camera access. However, the number of police-related shootings, complaints, and reviewed incidents have increased from 2014, and this is a trend that is continuing. And in 2021, there's increased tensions and a lack of confidence in modern-day systems. So, what is our solution? The EFFECT, the Engineered Future Enforcement Conduct Tool.
In order for our design to be successful, we need to make sure that it does not hinder a police officer's duty. This means it needs to be small and lightweight. Next, we need to make sure it actually fixes a problem. This is recording when a police uses a piece of equipment. So for example, if they draw their firearm at 5:15, it will record that a firearm was drawn at 5:15. Next, we need to make sure it remains cheap. In order for us to create an addition to body cameras and not put too much of an expense on larger departments, as well as getting a starting off point for smaller departments that cannot afford the body cameras by itself. And lastly, we need a database to keep track of all this information.
Now, our first concept. So our first concept was a holster button/lock system. So there would be a lock on a holster, and a button would have to be pressed to unlock it. When that button is pressed, a signal would be stated on a serial monitor, which would state at what specific time it was activated and which actual holster it was.
Our next design concept was the firearm safety button. When an officer would draw their firearm, they would have to push a button in order to use it, and this would record when the firearm is being used.
And this is the last design, which is the holster detection system. So there would be multiple sensors all across the utility belt of an officer, and each sensor would be placed on the specific holsters. Whenever any of these holsters are activated, when there's a specific sensor on it, it actually states on the serial monitor which specific time it was activated and which specific holster it was.
We decided to go with the hardware sensor, the holster detection system. This is because, unlike the firearm safety button and other options, it can record multiple infractions amongst different holsters, as well as we would use IR sensors to detect motion, as Fish was saying, to determine when a firearm was drawn or any other piece of equipment.
Now, the design process for the case. So on the top left here, you see our original design for the case itself. The problem with this original design was it was very bulky compared to what we have right now, and ultimately it did not fulfill the promises and our goals of what the design should be. So we transitioned to the cases we have here. We have a clip case and a magnet case. So we went through multiple different iterations. On the right you see the clip case, but we abandoned that idea because the clip case was becoming too flimsy. On the bottom right there, you see our modern day case units. We have a magnet case which is actually on the device right now with the Arduino chip inside, and we also have a secondary sliding case which we can use instead by removing this and putting the Arduino in that.
For the hardware part of it, as Fish was saying, we had two different designs for the casing itself. One would be a magnet case and the other would be a clip case. And as Fish was stating, right now we have it on the police belt itself, but it could be placed anywhere on the uniform to best fit an officer's needs.
Software. So originally we were using IR sensors using transistors and resistors. So whenever a transistor was near a resistor, it would record that action as an incident or an action recorded and state that on the serial monitor. Sadly, there were some difficulties with that. With the transistors and resistors, they have to be in direct contact with each other for them to actually record information because they are IR sensors. So in March 2021, we switched to PIR motion sensors. The motion sensors detect actual motion rather than transistors and resistors being in contact with each other. And due to the fact that they actually do detect motion, we're able to more efficiently record data and efficiently record motion and actions.
Here we have a picture of our circuit. On the left is where our Arduino Nano and all our wiring is hooked up. Once our design becomes final, we'll be able to design our own electronics board and make sure it remains small and compact. And on the right, we see the IR sensors that we are using.
So for the software, we had two original codes, both using the Arduino software. So the first code we used was a bit simpler. It was mainly just in a loop, and it did not have as many variables to control the different sensors and investigate each sensor's actions and recorded actions. The second code we had was a bit more varied. It had a bit more variables in determining which sensor would be active at what time and what they would record.
So, an explanation of our final design is that an officer every morning will plug in the lithium-ion battery to activate the device. The device will constantly be recording whether a sensor is detecting something or not. And if an infraction is made, that will be recorded. And once the police officer returns to the station, it can be logged down and reviewed.
So to record the information, we also created a database. For the software, we used a database software known as Quinta Database. So it is a bit blurry, I apologize for the image, but on the left here, we see the officer number, service hours, the service history in terms of total years, their infraction history, and the date and time of the last infraction. With a database like this, we have the ability to record information like this, so we can record actions, and we can record and inspect actual incidents. We also have different safety procedures and precautions in logging into the database, so no one can just go in and update. It has a specific set of guidelines to actually log in.
So how do we test our device? First, we wanted to see how we would be affected by it. So we started with running without the device and with the device on. Unfortunately, this had to be taken over the tests were taken 2 days apart, and there were slightly different weather conditions. But even still, we were able to see that the device barely affected us, and that in fact we ran faster around the courtyard with the device on than on average when we had the device off. Next, we wanted to keep it lightweight. Under 3 pounds was our original goal, and we far exceeded that. Each device is under a pound, with it being 214 grams for the magnet case and 165 grams for the clip case and now sliding case. Finally, we come to weatherproofing. Right now, both cases are unfortunately not waterproof yet, and as you can see in the picture, it is because of that gap there. That is left open for the wires, and once we finish our design, we can fully fill that in, but right now we're leaving it open for ease of use and changing our ideas, or changing our design if need be.
Now, the test of the detection systems themselves. So we have 3 specific sensors on the actual device, so we decided to record 5 separate tests, each recording the device in 10-second intervals. So the way this was tested is that our arms were put on all the holsters to see if they would be activated. They would be activated, and then we would run a 10-second interval to see how many times the device would record. So on average, from 5 tests in a 10-second interval, we have 40.2 detections per 10-second interval. This arises one of our testing problems. We have the ability to detect actions, but once actions are detected, we have no remedy right now to actually stop the loop and actually record the information in an efficient manner. We have the ability to record the information itself, but right now we cannot efficiently record the data in an accurate manner. So this would be an example of how on the serial monitor information will be recorded. So we see specific time frames here, and obviously, as I stated before, we do have problems right now with repeating data after first detections have been recorded and activated. On the right, you obviously see the different types of infractions pertaining to each different holster and each specific sensor.
So what comes next? Right now, we want to keep updating our software. As Vish was saying, we're having some problems with repeat infractions, even if it is not happening, so we want to make sure that that is fixed. Next, we want to fully weatherproof our design and make sure water can't get in. And we also want to decrease its size, which will all happen once we can create our own electronic board. And finally, we want to create a fully functioning police detection system.
Our goal for this device is to create an additional software system to body cameras and not necessarily as a replacement. With the new system in place, we have the ability to provide more information and more context whenever an incident happens, because right now, in many incidents right now, there's such a lack of information, and it becomes difficult to create a lot of reasoning. Thank you, and we hope you enjoyed our presentation.
Thank you, Caden and Vish. Presentation well done with 0 infractions. All right, presenting next with the Laundromate are Christian and Aiden.
Hi, my name is Aiden.
Hi, my name is Christian, and we're presenting our capstone project, Laundromate. The modern washing machine and dryer has made the process of cleaning clothes fast and easy. What once took hours of manual labor can now be complete with the addition of a few chemicals and the press of a button. However, even with these amazing devices, the average family still spends around 4 hours a week or 196 hours a year on laundry-related tasks. The laundry process of washing, drying, folding, and storing clothes, while necessary, is tedious, and the time and effort can be better spent elsewhere, which is why we are here today to present our solution on how to make the laundry process more efficient.
As Christian said, there are various problems with laundry, whether it's the amount of water you use or the amount of energy. But I think the biggest issue is obviously time spent. The average family spends about 4 hours doing 2 loads of laundry a week. And even in those loads, it's only filled to 70% capacity, wasting even more time and energy.
So we brainstormed several different solutions, each one addressing a different aspect of the laundry process. Up here is a concept sketch for what we called the smart hamper, and its job was to sort clothes based on light and dark color, since each has a different optimal wash setting. Ideally, once the hamper reaches a certain capacity, it would notify the user and then maneuver itself to the washing machine to unload its contents.
Our next design is the Keurig Washer. So there's hampers that go in the washing machine, and once the load is done, you just move them to the dryer. This process was to help speed up the transfer of loads and cut down the laundry time. The third device is the automated folding device. It has 4 panels connected by hinges. Embedded in the panels are 2 distance sensors, and when they are covered, the motors and panels will turn, causing the shirt to fold neatly at the top panel.
So in order to determine which design was best for our problem statement, we created a decision matrix, rating each design from a scale of 1 through 5 based on 5 different categories. Each category was given a weight multiplier depending on how important it was to our project criteria. For example, efficiency is given a weight multiplier of 3, since saving time is the crux of our problem statement. As you can see from here, the automated clothes folder won with a clear margin with a score of 35. We felt that in terms of simplicity and efficiency, it was far superior to the other 2 ideas. This conclusion was further supported in a survey in which we asked participants what is the most time-consuming part of the laundry process. Out of 162 responses, you can see that 80% pointed towards folding clothes.
With choosing laundry as our idea, we decided to look at previous attempts at the solution. We have the Laundromate, which folds the clothes by using rollers. The issue with it is it was very slow, and you still had to insert the shirt into it. The garment folding panels we actually liked a lot, and we liked it so much that we decided to improve upon it and try to automate it. Some of the criteria we look for in our project: customer needs, we look to cut down the laundry process by around 10%. Complexity, we wanted it to be easy to use, anyone can really use it. Maintenance, we wanted the product to last about 5 years, and we wanted the parts to be interchangeable so you could still fix it. Safety, we wanted to not only be safe for the user, but also for the clothes that are being folded. Materials, eco-friendly. And aesthetics, we wanted it to look good in a laundry room setting. And size and weight, about size of a
drying rack.
Sorry.
So now we're going to go over some of our prototyping.
The mechanical components, we have the panel, the hinge, and the axle. So the main thing was the hinge. It had to fit perfectly with the panel and the axle. So it was modeled on a CAD drawing and then 3D printed.
So for our electrical components, we opted to use the brand Rev, which was actually a robotics competition software or electrical components. We used the Rev hex motors and the color distance sensors, as well as the expansion hub. We originally were going to use Arduino, however, we had trouble finding compatible parts for what we had in mind. So instead, we went with this, and it saved us time on soldering and because we didn't have to make any permanent electrical connections, we could just plug and place. So for Rev, you have 2 options when it comes to coding. You can do block coding, or you can use the programming language Java. We chose to go with Java since we wanted a more sophisticated solution, and this provided us with more flexibility in how we wanted to tackle the software side of things. This is a snippet of the code here. The most important part is this if statement. So basically it says, if the distance sensor passes a certain threshold or is covered, then it'll trigger these 3 methods: fold left, fold right, and fold center, each of which correspond to a specific motor and a specific panel, and also their encoder values for more accurate positioning.
Here's our video of our prototype in action. As you can see here, the shirt is placed on the panel and it is folded neatly at the top. There's a frame at the bottom which we didn't discuss, but that was used for the prototype as to just hold it up in the air so the motors and the sensors could be in the right spot. In this test, we folded 5 shirts and recorded the time. Here are our testing results. You're probably wondering, is this actually faster than folding clothes manually? Based on our results, it is not faster by about 25 seconds. However, this may seem discouraging, but our main goal was to aim for automation and not speed, because we have 2 more components that we look to integrate in the future that will hopefully, when created, eliminate human interaction as much as possible and eventually cut down the laundry process.
Unfortunately, we weren't able to make physical prototypes of the other 2 components, but we prepared some 3D simulations to show you guys what we had in mind. So pictured up there is what we call the hanger removal device, and as the name implies, it's designed to remove a very specific type of hanger, this one. So how it works is the hook of the hanger is situated on that cylindrical red knob protruding upwards. From there, the 2 yellow parts on each side are mounted on vertical sliders. We'll press down on the clamps of the hanger, releasing the t-shirt. The red part, or the horizontal slider, will then pull the hanger away from the clothes. The idea is to mount this hanger removal device on the folding device we showed in the last video. So that way you can remove the hanger and then immediately fold the t-shirt. Now with the hanger, we need something to hang it on, and that's where our 3rd component comes in, called the moving rack. Now, the moving rack's main goal is to transfer t-shirts to the other 2 devices. And this green rectangular piece represents the combination of the hanger removal and the folding devices. So the moving rack will be automated to move multiple shirts down this line until it reaches the other 2 devices, where it will then pass it off. If you recall that red protruding knob, that's what we're aiming for the hangers. So the 2 devices will receive the clothes in a vertical position. Now obviously you can't remove the hanger from there or the t-shirt will fall to the ground. So as shown in that video, this will rotate into a horizontal position. And from there, it can remove the hanger and then perform its folding sequence. Ideally, the 3 components, the folding device, the hanger removal device, and this moving rack will be integrated as one, to the point where the only human interaction should be you hanging the t-shirts on the rack.
Our future plans are to create all 3 of these prototypes and then integrate them together. And then with that product, we will hopefully solve the problem of laundry.
Thank you for listening.
Thank you for your time.
Thank you, Aiden and Christian, for a nice, clean, and efficient presentation. And presenting next, our final presentation is going to be the ProTracker presentation by Chris Bauer and Jonathan Yao.
Oops. Good evening. I'm Chris Bauer.
And I'm Jonathan Yao. Our project, the ProTracker, is a device designed to help referees monitor football activity during games.
Here's the problem statement we were originally working to solve. NFL referees are unable to accurately and consistently determine first downs and touchdowns due to the inability to coordinate the position of the football with the downing of the ball carrier during gameplay. This is due to the fact that officials are expected to spot the ball using only their eyesight, with video review only applying when a coach challenges. Once the ball is spotted, a 10-yard chain is used to determine if the ball has crossed a first down marker. Incorrect first down and touchdown calls upset fans, NFL analysts, and NFL personnel. This problem occurs in football games throughout the country, and problems like these can be found in almost every game. According to the NFL officials make wrong calls 4.3 times per game on average. And many of these errors could be easily eliminated by addressing this human error. Additionally, These errors occur despite 20+ hours of preparation each week by NFL officials, which leads to dissatisfaction among fans and players and financial losses by the NFL and its teams.
So the Pro Tracker first addresses this problem by improving game flow and meeting customer needs. As an avid NFL watcher, I know games are interrupted enough by advertisements, so we wanted our device to relay information to the serial monitor within 1/2 of a second to keep the game moving. Another design requirement we implemented is reusability and low maintenance during games. To operate the final product, we wanted the cost per game to be less than $306 because that's the cost of traditionally measuring down and distance and performing football analytics. Our display should be clear and appealing, and the football appearance should not be compromised. Lastly, we want the system to be as automated as possible. So with the requirements set, we began brainstorming. This is a combination of the mobile first down marker and an RFID system, so when the ball passes the first down plane, the down indicator will be reset and the down marker will automatically move to the new position of the football.
This idea was a drone with an RFID sensor that could track the football and follow the football. And when the play was over, the referee could stop the drone's motion and turn on a laser pointer which indicated where the nose of the football should be placed.
Our other idea is a monitor that uses a RFID map to track live player location as well as the place where they have been downed on the field.
While these 4 ideas, including the one you see above, can all solve the problem, we had to choose one idea to pursue. To do this, we used a decision matrix which ranked the ideas based on different criteria, and this was our planned solution to develop. There would be 2 RFID sensors behind the end zone and 2 at midfield. They would be able to triangulate the position of tags inside the football and on the player's knees and elbows. This would create a live map of where the football is on the field. The officials would be tasked with spotting the football by finding where the ball carrier's tags had an altitude of 0 and then identifying the location of the football at that time.
So after we performed brainstorming, we had to conduct research on RFID technology. What we found was that active RFID was beyond our budget, so we had to stick with passive RFID technology. So we used a SparkFun Redboard, an antenna, a passive RFID reader, and a passive RFID tag to set up our testing system. We found that the maximum range of the RFID system was only 6 inches, and that's not feasible for an actual football game, so we had to find other measurement methods.
We then researched more regarding Bluetooth tracking because a recent version of Bluetooth allows users to find the position of a Bluetooth beacon within centimeters of accuracy, which is perfect for our goal. Additionally, the range of Bluetooth would theoretically cover the entire football field. However, we learned that since this technology is so new, none of the softwares designed for the general public are able to track Bluetooth beacons using angle of arrival, which is the new technology we needed to get these accurate readings.
So our final method of measurement was using an accelerometer. We wanted to use calculus to determine the distance traveled by the football. We ordered 3 accelerometers so we could use a process known as Kalman filtering to find more accurate data. Due to time constraints, our goal was to only track the football's position. And after soldering jumpers to the accelerometer, the ADXL345, and pins to the Arduino Pro, we could begin testing.
In order to relay information to the computer, we needed a system of wireless communication. We decided to begin with Wi-Fi, but found this to be too complex and time-consuming, so we went with radio communication instead, which is simpler. We attached an antenna to the radio transmitter and receiver to increase the range. We then designed an enclosure, which you can see there, and that was designed to sit inside the football and protect the components, including the antenna, from impact and the elements.
Of course, there were many other steps we had to take while testing components of the prototype. As we previously described, the maximum range of the RFID system was only 6 inches, which we determined experimentally by taking an RFID tag and moving it farther and farther away from the antenna until we stopped receiving readings. Another test we had to do was using the accelerometer. With the accelerometer, the ADXL345, plugged into the Arduino Pro, plugged into the laptop, we ran the calibration code. It displayed the accelerometer values after pressing a button, which showed that the accelerometer was working.
We reviewed the calibration code and took readings to calibrate the accelerometer. Using data from the serial monitor, we inputted values into the equations that you could see here, and we got our offset and gain values, which we then put into the calibration code to calibrate the accelerometer. When we were ready to test the system's success, basic testing showed that the position data from the accelerometer was inaccurate and unreliable due to small errors that were propagated throughout our calculations. With only 3 weeks remaining to finish the project and submit testing results, we decided to modify our problem statement and the purpose of our system. Mr. Cohen, one of our engineering mentors, suggested that we change the objective to something more manageable, to identify interference with the motion of the football. This could be useful in determining if a defender tipped the ball, if the flight of the ball was interrupted by a gust of wind or the sky cam, as you see there, as well as when the ball is caught or when it hits the ground, which would stop the game clock.
As a result, we had to set up additional guidelines for tests. In our Arduino to computer wireless communication test, we printed Hello World from the Arduino to a computer serial monitor wirelessly. We achieved this using radio transmission. We also ran a test with a single accelerometer to detect activity. So the Arduino will print activity when the accelerometer is accelerating and inactivity when the object is not moving. This test was also successful.
We tested the enclosure to make sure that the data was transmitted correctly through the enclosure and to ensure that the components were correctly protected inside the enclosure. The components fit properly, and when the accelerometer was moved inside the enclosure, the serial monitor reported the activity. The enclosure held upon impact.
Criteria used to determine if our device passed or failed to address our problem statement includes if the device can detect football activity, if it can display the activity status on the serial monitor, if it can update the status using timestamps on the monitor, and if it required little maintenance. Our procedure for testing included calibrating accelerometers inside the football, throwing and catching the football 10 times, throwing the football and batting it to the ground 10 times, and throwing the football and letting it hit the ground 10 times. Then we will analyze the activity statuses to determine if the accelerometer's data can effectively determine football movement.
The activity was successfully registered on all 10 of the catches, 8 out of 10 of the incompletions when the ball was allowed to hit the ground, and 8 out of 10 of the deflections when the ball was batted or tipped out of the air. These failures to detect the activity were likely caused by the battery dying or the jumper wires disconnecting, which happened 3 times and 1 time respectively. We found that switching between our 9-volt batteries addressed the battery problem, while the jumper wires simply needed to be reinserted. The transmission was very quick, and the data showed on the display in well under half a second in all trials. The weight of the football was not significantly different, but the handling was awkward because of how the prototype was constructed. A smaller version of our system inside of a real football should address this problem.
Overall, our project was a successful integration of advanced Arduino coding and physical components to develop a system to report ball activity statuses during game simulated motions. However, it can be improved by implementing non-commercial microcontrollers and circuit boards to make the device more compact and lightweight and to keep the wires more secure, because a breadboard would not be needed. This will also make the football more aesthetically pleasing than our current prototype. We can make the receiver system more portable so referees can carry the system and access the user interface at any time, even on the field. Furthermore, either the power source or the system's power efficiency must be improved because it can only operate on one battery for minutes at a time. Nevertheless, this is encouraging progress during an unconventional year. For example, the reason distance tracking was so difficult was not because we didn't understand the theory, but because the Arduino cannot do double integration in small enough intervals for the distance displayed to be accurate. So with better technology and more time, our next steps will be to make a compact system that can employ calculus to determine distance traveled by the football. That will be a huge step in improving the game of inches we call football. We appreciate your attention, thank you for your time, and have a good night.
Thank you, Jonathan and Chris. So at this point, I'd like to welcome Mr. DeJulius back up to make some closing remarks.
Thank you, Mr. Condorso. Let's have another round of applause for the students. Okay, at this time, I'm pleased to report that all of the projects this year have met all of the criteria set forth by the faculty and are worthy of acceptance for this year's Project Lead the Way class. Congratulations. So at this time, we're going to present the students with their honor cords. And students, please wear your honor cords at graduation to represent your participation and completion of the Project Lead the Way program.
Cherry Abraham. Ian Camerado. Caden Conklin. Aiden Greenberg. Mackenzie Lippincott. Krisha Mahajan. Vish Patlala. Sajan Shaw. Chris Bauer. Christian Apostle. Aiden McCarty. Jonathan Yao. Alexa Zuberlov. Well done, PLTW class of 2021. I'm in awe of the students' dedication and enthusiasm to solving problems, especially given the circumstances of this past school year. I know that this wasn't like the top thing to do on their list at maybe any point in time during their senior year this year with all these extenuating circumstances, but they did it, and they didn't just do it to get it done. They did it with, as I said, enthusiasm and to the best of their ability. The intent of the PLTW program is to create an opportunity for students to hone their skills to become real-world problem solvers. Based on all the work that they've done this year, they've shown that they're capable of solving problems. I didn't want to say anything to all of you prior to this evening, but you had a really challenging scenario of presenting this year. Typically, during the course, we have live presentations, kind of working our way up. We start in the LGI, we do a couple presentations there, and then we work our way up to kind of the main stage, high-stakes capstone presentation. And this year, things were kind of in reverse. Students had done pre-taped presentations that they were sending off for people to view throughout the course of the year, and then things really ramped up at the end. So I want to congratulate you again and let you know I'm so proud of what you accomplished, and I'm very much looking forward to all that you're going to accomplish in the future. Thank you. I also want to thank all of the families that have supported the students, not just this year, but throughout high school and throughout all the Project Lead the Way projects and software programs and glitches and everything else that I'm sure you've heard about. I want to thank my fellow Project Lead the Way teachers for continuing to improve the Project Lead the Way program and make it better every year. I want to thank the science department, the tech ed departments just in general, and also the school administration and everyone else that has helped out, the professionals that dedicate their time selflessly every year to give feedback to students and help them improve their projects.